Thank you for the introduction, and hello everyone. In following talk, I'm going to show you our study, which is frequency-dependent tACS modulation of both signal during rhythmic visual stimulation. First, I want to introduce some backgrounds. As you may know, previous MEG researchers have showed that tACS could modulate brain oscillations in a frequency-dependent manner. Some researchers have applied tACS to target occipital cortex, and they found alpha activity could be increased by tACS if it's applied at individual alpha frequency. In addition, if they applied rhythmic visual frequency at the same time with tACS, they found that the frequency-induced steady-state response could also be changed if the frequencies of tACS and visual stimulation are same, and will not be changed if the frequencies of these two stimulations are different. These researchers tell us clearly that tACS modulation of brain oscillations is determined by the frequency relationship between tACS and brain oscillation. But they didn't give us much information about the spatial distribution of this tACS modulation. We know function MI could do much better in this aspect. Up to present, there are very few concurrent tACS function MI studies, and none of them has tested this steady-state response tACS frequency-dependent interaction. So in our study, we combined the rhythmic visual frequency and tACS, and used the function MI to explore first the frequency-dependent tACS modulation of SSR-related board signal. So we know that visual checkboard frequency will induce a board response in visual cortex. If we apply the tACS with a same frequency, at a same frequency with the visual checkboard frequency, we expect the visual board response, the amplitude of visual board response will be changed by tACS. If we apply the tACS at a different frequency with the visual stimulation, we expect to see no change in the visual board response. And in addition, with function MI, we will certainly have a special distribution of this tACS modulation. So here is the experiment design. We put two tACS electrodes, one on OZ, the other on CZ, to target visual cortex, and applied 1 milliamp sinusoid current. For the visual stimulation, we used the checkboard of 25% contrast level to avoid the ceiling effect of board response. And in every function MI run, we applied a block design with 13 seconds period for both the rest and the flick block. And tACS was only applied during every other flick block. We applied this pattern repeatedly for 6 times in each function MI run. And we designed 2 experiments. One is 8 Hz flick experiment, in which we applied visual frequency at 8 Hz in all 3 runs, while tACS was applied at 4 Hz in run 1, 8 Hz in run 2, and 16 Hz in run 3. The other is 16 Hz flick experiment, in which we applied visual frequency at 16 Hz in all 3 runs, while tACS was applied at 8 Hz in run 1, 16 Hz in run 2, and 32 Hz in run 3. The order of these 3 runs was randomized in different subjects of each experiment. And we acquired the function MI data on 3T using simultaneous multi-slice grid echo EPI with TR of 2 seconds and the voxel resolution of 2 millimeters isotropic. In data analysis, we subtract the visual board response with no tACS from tACS own condition to extract tACS effect or contrast. So here is the result from 8 Hz freak experiment. First, only 8 Hz tACS increased 8 Hz freak induced board response in the cuneus and mid-occipital gyrus bilaterally, while 4 Hz and 16 Hz tACS had no effect here. When compared to 4 Hz and 8 Hz, 16 Hz tACS, which had no effect, we found that the 8 Hz tACS still showed significantly stronger positive effects in this same area. If we extract the median tACS contrast value from these red visual regions, which were activated by 8 Hz visual stimulation, you can see it clearly that only 8 Hz tACS increased the 8 Hz freak-induced board amplitude. And when compared to 4 Hz tACS effect, 8 Hz tACS still showed a significantly stronger positive modulation effect. Now let's move to the results from 16 Hz freak experiment. Both 16 Hz tACS and 13.2 Hz tACS decreased the 16 Hz freak-induced board response in these visual areas, while 8 Hz tACS had no effect here. When compared to 8 Hz tACS, which had no effect, we found that both 16 Hz and 13.2 Hz tACS showed a negative modulation effect in this visual region. And if we extract the RI median tACS contrast value from these red regions, which were activated by 16 Hz freak stimulation, you can see it clearly that both 16 Hz tACS and 13.2 Hz tACS decreased the 16 Hz freak-induced board response amplitude, while the effect of tACS at 8 Hz was not significant here. So to conclude, I hope I have showed you that tACS modulated the visual board response when tACS frequency matched the freak frequency or the second harmonic frequency. First, 8 Hz freak-induced board response was increased by 8 Hz tACS. Second, 16 Hz freak-induced board response was decreased by 16 Hz or 13.2 Hz tACS. And in addition, the main tACS effects were seen in regions like cuneus or mid-occipital gyrus. These regions were also activated by visual freak. And these regions were also the areas which are expected to have the highest tACS current density based on previous study. At last, I want to thank my advisor and collaborators from Peking University and NIMH. And welcome to my post if you are interested in more details. Thank you very much.
Very nice work. Now let us invite questions or comments from the floor.
So you did some concurrent tACS diaphragm study, right?
Yes.
Did you do some testing before the true experiment?
Yes.
I mean, by some phantom. What about the data quality?
You mean like tACS if we see some tACS artifacts? Or?
Yeah.
Okay. There are some previous studies have studied the tACS current itself, the effect of tACS current itself on the function MI signal. So I think there are 2 points here. First, in the time domain, they found that tACS didn't cause the tACS current itself didn't cause any function MI signal change in the time domain. But in the spatial domain, tACS may decrease the signal to noise ratio in the image. But in our study here, we didn't see any tACS artifacts here.
New artifact.
Yes.
Okay, thank you.
Thank you.
Okay, next, please.
I apologize if I missed this from your talk. I'm just wondering if you controlled for the phase of the tACS
I didn't,
relative to the visual stimulus. I ask because there's a lot of evidence to suggest that in tACS experiments, the phase of the simulation has an important role on the effects of neural activity.
I agree with your idea. We didn't okay, so let me answer your question in this way. We only synchronized the time of tACS stimulation and visual stimulation. But we know there's a delay time between the visual stimulation and its evoked neural response. This delay time is about 40 milliseconds. And so there will be a relative phase between tACS and the visual response. And as I show you, you may ask why the tACS effects at 8 Hz and at 16 Hz are opposite. One possibility is just as you said, is because of the phase effect. Because if we assume the delay time between visual stimulation and the visual response is the same in both experiments, like 14 milliseconds, the relative phase in 16 Hz freak experiment will be twice larger than in 8 Hz freak experiment, because the period of 8 Hz is twice larger than the period of 16 Hz. So I agree with you. And in our experiment, we didn't synchronize, we didn't study specifically on the phase, but I think it has effect here.
Thanks.
Thank you.
Okay, thank you very much, Dr. Chai.